Hello students, let's go back to section 3. The second half of section 3 is basically the optional part of an optional section. So go figure, it's gonna be hard. Okay, let's begin. And let's begin with a brief recap of what we discussed previously. We begin with a homogeneous linear ODE with constant coefficients and its characteristic polynomial. And we define the set RQ and EQ. We define RQ as a set of all proper rational expressions whose denominator is Q of S, the characteristic polynomial. Here, proper rational means the degree of numerator is less than the degree of denominator. It turns out RQ is a linear space, and indeed we proved it. EQ, on the other hand, is defined as an image of RQ under the Laplace inversion. It turns out EQ is also a linear space, and of course, we proved that too. Furthermore, we proved that EQ happens to be the solution space of the original homogeneous ODE, this one. This course is about differential equations, so we're always headed towards solution. And indeed, in this section, our aim is to analyze EQ, the solution space. Now, how do we analyze it? The main tool here is this one, the standard basis or the standard basis functions. It turns out B of EQ, defined like this, is a basis of this linear space EQ, and thus it generates everything in EQ, and also these are linearly independent. Now please recall, EQ is actually a solution space of the original homogeneous ODE. That means any solution of this homogeneous linear ODE is written as a linear combination of these basis functions, and also vice versa. Any linear combination of these basis functions is a solution of this original homogeneous equation. Moreover, that linear combination expression is unique. That's because these are linearly independent. Okay, I guess we covered pretty much everything other than the proof. Oh, excuse me, no, not really. We have to discuss how did it get these functions. Okay, let's go back. Let's go back to the original linear ODE and its characteristic polynomial, which was defined from the coefficient structure. Now, let's apply the fundamental theorem of algebra. Then, we can factor any polynomial all the way down to the linear factors, the way we see over here. Here, the complex numbers lambda 1, lambda 2, lambda 3, and so on are called the zeros, and the positive integers m1, m2, m3, those are the multiplicities. And the fundamental theorem of algebra applies in the complex field, so the zeros are in general complex numbers. Luckily, some may be real, but in general complex. And the multiplicities must add up to the degree of the polynomial n, because if you look at the right-hand side, what's the degree? You have to add up all these powers, m1 plus m2 plus m3 plus and so on. Now, if you look at the left-hand side, the degree is n. So yes, if you add up these powers, if you add up these multiplicities, then we have to have n. Now keep those in your mind, and let's go to the first line here. We claim that B of RQ, given by 1 over s minus lambda 1 to the first power, second power, third power, all the way over to m1th power, and then same pattern repeating to each factor like this, is a basis of RQ, and their Laplace inversions form the basis of EQ. Those are my claims. Let's go back to the first line again, and let's count this time. How many red fractions are there? 1 over s minus lambda 1 to the first power, second power, third power, all the way over to m1th power, so there are total m1 of them. And then the next color, which corresponds to next factor, and in the end we have the last factor highlighted in green. And then come back here, 1 over s minus lambda k to the first power, second power, third power, and so on, all the way over to mkth power. We get this. Repeating all those and adding up all those, we have precisely n functions because of this. So if we establish that this is a basis, then basically we're establishing this one as well. The dimension of RQ is n. Now from here, from these fractions, take the Laplace inversion and get these functions, and reclaim these form the basis as well. Please remember, EQ was obtained from RQ through Laplace inversion. That was the definition, by the way. Okay. Alright, finally, I got everything done besides a proof. Okay, shall we go ahead and prove it? No, one more comment beforehand. Let's come back to the dimension. Now, dimension is n. What does it mean by that? Well, any linear space has multiple bases, but each time we have the same number of basis elements from each base. So that's the dimension. And also, the dimension is the minimum number of generators and also the maximum number of linear independent elements in a family. So, if you end up with any n linearly independent solutions of the original, then those n functions will have to form the basis. It may be a different basis than this one, but that's okay. It's a basis too. That's coming from the dimension analysis. Okay, I guess so. That's about it. I think I did everything that is necessary except actually proving these. Let's see, did I forget anything? No? Okay, alright, let's go. Let's go to the proof. We have to prove that eventually this is a basis, and that means we have to prove that this set spans or generates entire solutions. That's part 1. And part 2, this family is linearly independent. That's going to be a bit harder. Now our aim is EQ and analyzing EQ, but as an intermediate step, we're going to do this one first. Get this one done first, and then shift it over to this through Laplace inversion. That's the plan. Okay, let's begin. Let's go ahead with the first line here. Let's prove that these fractions generate or span entire RQ. That is, any element here, any element, arbitrary element, R of S over Q of S, by the way, that's the definition. Yes, any element here can be written as a linear combination of these fractions. Okay, ready? Here we go. It follows rather easily from the theory of partial fraction. The degree of denominator is bigger than the degree of the numerator, so we don't have any integer part or any quotient part. So we have this strict decomposition by partial fraction based upon the factorization of the denominator, which is right here. Okay, alright. So much for this set generating entire RQ. Now, from here, let's take the Laplace inversion and let's see what you're going to get. So the arbitrary element of EQ looks like this. Let's go back to the definition of EQ. It was defined through the Laplace inversion of RQ. An arbitrary element of RQ looks like this, R of S over Q of S, and then take the Laplace inversion there. So the arbitrary element is of this form. Laplace inversion of R of S over Q of S. And we know about R of S over Q of S from this decomposition by partial fraction. So let's take the Laplace inversions. And then what we get? We get these. T to the 0 power, e to the lambda 1t, and t to the first power, e to the lambda 1t, t to the second power, e to the lambda 1t, and so on, all the way over to t to the m minus 1, e to the lambda 1t. And please recognize the denominators here. We have these factorials. Many times, most of the times actually, I used to change the characters to something else, but this time it is necessary, so I went through all this to the detail. So okay, in the end, what did you get? The arbitrary element of EQ, or equivalently speaking, arbitrary solution of this homogeneous linear ODE with constant coefficient, can be written as a linear combination of these functions. Okay, the first half is done. Let's go to the other half, which is going to be a bit harder, the linear independent. Basically, what we want is to set up a linear combination of those equal to 0 constantly, and then we have to prove all the coefficients are 0. But then again, it's going to be difficult to deal with this directly because there are so many transcendental functions here. We'll do this first, and then push it through the Laplace inversion. Okay, here we go. Let's set up like this. The linear combination of these fractions is equal to 0 constantly. Okay? And then, here's an ingenious technique. Multiply by the denominator, the largest denominator, s minus lambda k to the mk power. Multiply that to both sides and distribute around. Then that's equivalent to multiplying the same factor to each of them. And for the last one here, the entire s minus lambda k to the mk power will cancel each other out, and I'm going to get only the coefficient here, ck of mk. Alright? How about the next one here? Mk power and then mk minus 1 power. So I'm going to get 1 power of this s minus lambda k left. And then and so on and so forth. Here mk minus 1. In any case, some of this s minus lambda k factor will stay. As for the other colors, other factors, I don't care at all. So s minus lambda k to at least 1 power is common to everything, so factor it out and you have something left. Okay, so this part becomes that, and all the other parts here ended up with this. Now we're going to take the limit as s is approaching to lambda k. Why don't we just plug it in? We can't. Look at this expression. Lambda k is, s minus lambda k is in denominator. So if you just plug in, this expression here in the left-hand side may not be well defined, but if you take the limit, then it's okay. And look at the limit rule. That's something that algebraic expression has no denominator of this green type. Those, they all canceled out. Okay. The other denominators, s minus some other lambdas to whatever, I don't care because s is approaching to lambda k. And then this is going to 0. So what do we have? 0 times something plus this coefficient is equal to 0. So the last coefficient is equal to 0. We get that. Ooh, we have to prove all the coefficients are equal to 0, but we are done with only one. The last coefficient is equal to 0, and it looks like we went through a lot. Looks like we still have a lot more coefficients to work on. But as a matter of fact, no. We are 90% done. More than 90% done, actually. The last coefficient is 0, so basically this one drops out. And we can apply exactly the same idea to the next largest, and then kill, and the next coefficient is 0, basically. So multiply s minus lambda k to the mk minus 1 power to each, because that doesn't exist anymore because this coefficient is now 0. Throw that away. We are working with only these and work exactly the same way. Then we have this constant left, and then to the left we have s minus lambda k times something. Upon taking the limit, again we have 0 plus the constant is equal to 0, so we have that coefficient equal to 0 again. If you just repeat it, and then from the right, you can take all the coefficient becoming 0, 0, 0, 0, 0, all the way to the left, and then you're going to get all 0. Okay, this completed the proof of the linear independence of the first line. We already proved that this set generates entire RQ. Now we prove that this set is linearly independent as well. So this is the basis, a basis, and we're going to call it the standard basis. Now, how about the standard basis for EQ? We have to prove that this is a basis as well. We're done with the fact that this generates. Okay, all right. How about the linear independence? Okay, all right. Let's set up the linear combination equal to 0 constantly. And then let's apply the Laplace transform. So this becomes that, and so on and so forth. This becomes that, and so on and so forth, upon taking all those Laplace transforms. And then we get the coefficient which was there before, and then factorial over s minus lambda to appropriate power. Toward the end is factorial over the power. We get all those. For all those factors with all those color coding. Now, we already proved that this is linear independent family. So all the coefficient, all the numerator is equal to 0. So yes, we have to have all the coefficient equal to 0. Now this kind of computation has to be precise, so I use all the all the factorials here to get precise expression. Can be a bit confusing, but in the end, we get all these. So if you're unsure about these factorials and stuff, you can always go back and look up this Laplace table in page 123 of our textbook.